Hello, in this lecture I answer two questions. In the first question, find out the area of this green shape, and in the second question, find out the area of this square ABCD using three different methods. So let's start with the first question. In the drawing, we have a circle that is inscribed by this triangle ABC. You know that side AB of triangle ABC equals to 6 units in length, side BC equals to 9 units in length, side AC equals to 7 units in length. Again, our task is to find out the area of this ring shape. So first of all, we define angle ACB. This angle is theta. And we'll implement the law of cosines in this triangle ABC. Repeat quickly on the law of cosines. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to 9 units in its length, side BC equals to 3 units in its length, side AC equals to B units in its length. This is angle BAC that equals to theta degrees in its side. According to the law of cosines, the following equation is true. Cosine theta equals to a squared plus b squared minus c squared, or 2 times a times b. Again, cosine theta equals to a squared plus b squared minus c squared, over 2 times a times b. So we can implement the law of cosines in our drawing. Implement the law of cosines in triangle ABC. According to the law of cosines, cosine theta equals to AC squared plus CB squared minus AB squared over 2 times AC times CB. So the norm. Cosine theta equals to AC squared plus CB squared minus AB squared over 2 times AC times CB. Repeat again, in this triangle ABC according to the law of cosines. Cosine theta equals to AC squared plus CB squared minus AB squared over 2 times AC times CB. So cosine theta equals to AC squared. AC is 7. And therefore AC squared is 7 squared. Plus CB squared. CB is 9, therefore CB squared is 9 squared. minus AB square. AB is 6, therefore AB square is 6 square over 2 times AC is 7 times CB. CB is 9. So today we found out that cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. So cosine theta equals to 7 square. 7 square is 49 plus 9 square. 90 square. 9 square is 81. Or 6 square. 6 square is 36. Or 2 times 7 times 9. 7 times 9 is 63. And 63 times 2 is 126. So in total we actually found out that cosine theta equals to 49 plus 81 is 130 minus 36 over 126. Cosine theta equals to 130 minus 36 over 126. So cosine theta equals to 130 minus 36 is 94 over 126. $94 over 126 is equal to 0.7169. So in total we found out that cosine theta equals to 0.7169. We would like to find out the size of angle theta, or the value of angle theta. In order to find out the value of angle theta, we will operate the opposite function of cosine, that is r cosine, on the result of cosine theta, that is 0.7169, and this way we get the value of theta itself. So r cosine, the opposite function of cosine, of the result of cosine theta, that is 0.7169, equals to angle theta itself. R cosine 0.769 equals to 40.368 degrees, and it is equal to theta. So theta equals to 40.368 degrees in its size. Therefore 180 degrees minus theta equals to 180 degrees minus 40.368 degrees. It is actually 139.632 degrees. Then again, we found out that 180 degrees minus theta equals to 139.632 degrees. In the next step, we define the center of this circle. This point is point O. We define the point of tendency of tangent BC with this circle. This point is point L. Likewise, we define the point of tendency of tangent AB with this circle. This point is point Q. And finally, when we find the point of tendency of tangent AC with this circle, this point is point P. We define the radius of this circle as R, and we join points O and L together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle, is equal to R according to our definition. So here we can implement rule 1, where for the radius of L is equal to R, the radius of L is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we join points O and P together by a straight line. OP is of course the radius of the circle that is equal to R. Point P is the point of tendency of tangent AC with this circle, and therefore according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So actually, when doing this construction, we created quadrilateral POLC. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. So which angles we have in quadrilateral POLC? We have 90 degrees plus 90 degrees is 180 degrees, plus this angle theta, plus this missing angle POL. In total, the sum of those four angles must be equal to 360 degrees according to the rule that I mentioned. Repeat again. In quadrilateral POLC, the sum of the angles must be equal to 360 degrees. That is to say, 180 degrees plus angle theta plus the missing angle POL, in total must be equal to 360 degrees. Here we subtract 180 degrees from this equation. So here 180 degrees will get cancelled, and you left only with theta in this side of the equation. You left only with theta plus the missing angle POL is equal to 360 degrees minus 180 degrees is 180 degrees. So theta plus the missing angle POL equals to 180 degrees. Here we subtract theta from this equation. And we get that the missing angle POL is equal to 180 degrees minus theta. So here, this is the missing angle POL is equal to 180 degrees minus theta. But we already found out that 180 degrees minus theta equals to 139.632 degrees. So I get POL equals to 100 degrees thermostat equals to 139.632 degrees in its size. In the next step, we will implement rule 2 on triangle ABC. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common point to a circle are equal. So in the drawing, we have a circle. This is the common start point P. From this common start point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. First of all, we define the length of line segment VL as A. And we will focus on this common start point B. From this common start point B, we have two tangents to this circle, tangent BL and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BL equals to BQ. But BQ equals to A, therefore BL equals to A. According to the definition, therefore BQ must be also equal to A since then. AB equals to 6 and BQ equals to A. So AQ in total equals to AB, that is 6, minus BQ, that is A. So in total AQ equals to 6 minus A units in its turn. Side VC equals to 9 units in its length. AEL equals to A units in its length. Therefore, the missing line segment LC equals to BC, that is 9, minus BL, that is A. So in total, LC equals to 9 minus A units in its length. In the next step, we focus on this connection point A. From this connection point A, we have two tangents to this circle, tangent AQ and tangent AP. And according to rule 2, they are equal to each other. That is to say, AQ equals to AP. But AQ equals to 6 minus A, therefore AP must be also equal to 6 minus A units in its turn. In the next step, I focus on this connection point C. From this connection point C, we have two tangents to this circle, tangent CL and tangent CP. And according to rule 2, they are equal to each other. That is to say, CL equals to CP, but CL equals to 9 minus A, therefore CP must be also equal to 9 minus A in its length. It gives us the question that side AC of triangle ABC equals to 7 units in its length. AC consists of two line segments, AP and PC. Therefore, AC must be equal to the sum of the two line segments that it consists of. That is to say, AC must be equal to AP plus PC. So AC equals to AP 6 minus A plus PC is 9 minus A. So in total, AC equals to 6 plus 9 is 15. Minus A is minus 2A. So in total, AC equals to 15 minus 2A. AC equals to 7, so we substitute AC by 7. And we get that 7 equals to 15 minus 2A. Here we will add 2A to this equation and we will subtract 7 simultaneously. And we get that 2A equals to 15 minus 7, that is 8. So 2A equals to 8. Here we divide this equation by 2 and finally we get that A equals to 8 over 2, that is 4. A equals to 4 units in its length. So actually, this is the answer at the end, that equals to A, and A equals to 4. QB also equals to A, this equals to 4. AQ equals to 6 minus A. 6 minus A, 6 minus 4, that is 2. Here, AP equals to 6 minus A, that is 2. PC equals to 9 minus A. 9 minus A is 9 minus 4, that is 5. LC also equals to 9 minus 8, that is 5. In the next step, we will find out the semi-perimeter of this triangle ABC. The semi-perimeter of any triangle equals to the perimeter over 2. And the perimeter of any triangle is equals to the sum of its 3 side lengths. In this case is AB, that is 6, plus BC, that is 9, plus AC, that is 7. So the semi-perimeter of triangle ABC, S is a proportion for semi-perimeter. So S, the semi-perimeter S equals to the perimeter, that is actually 6 plus 9 plus 7. Over 2. 6 plus 9 is 15, 15 plus 7 is 22, 22 over 2 is 11. So total we found out that the semi-perimeter S of ABC equals to 11 units in its length. In the next step, we will find out the area of this triangle ABC according to a special formula. The area of any triangle according to the special formula is equal to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of the triangle, in this case S equals to 11. And define side AB as A and A equals to 6. We define side BC as B and B equals to 9. we define the length of side AC of triangle ABC as C, and C equals to 7. And again, A equals to 6 because B equals to 9, C equals to 7, and the semi-perimeter S of triangle ABC, the semi-perimeter S of triangle ABC equals to 11 units in its length. So, the area of our triangle ABC is equal to the square root of S is 11, times S minus A. S is 11, 6 is A is 6, so S minus A is 11 minus 6, that is 5. Times S minus B. S is 11, B is 9, so S minus A is 11 minus 9, that is 2. Times S minus C. S is 11, C is 7, S minus C is 11 minus 7, that is 4. So in total, we found out that the area of triangle ABC equals to the square root of 11 times 5 times 2 times 4. The square root of 4 is 2, so we take 4 out of the root. We get that the area of triangle ABC equals to the square root of 4, that is 2. Inside the root, we left only with 11 times 5 times 2. So in total, the area of triangle ABC is equal to 2. Inside the root, we have 11 times 5 is 55, and 55 times 2 is 110. So in total, we found out that the area of triangle ABC equals to 2 times square root of 110 square root inside. Triangle ABC blocks this circle. Well, this circle is inscribed by triangle ABC. Actually, we have a special formula for the area of a triangle that blocks a circle. Again, we have a special formula for the area of a triangle that blocks a circle. According to the special formula, the area of a triangle that blocks the circle is equal to S times R. S is the semi-perimeter of the triangle that blocks the circle, and R is the radius that is inscribed by the triangle. We already found out that the area of triangle ABC equals to 2 times square root of 110 square root in size. And it is equals to S. S, the semi-perimeter S equals to 11 units in its length, times the radius R. The radius R is the missing variable. R is the radius of this circle that is inscribed by triangle ABC. So in total, we found out that 2 times square root of 110 equals to 11 times R. Here we divide this equation by 11 and finally get that the radius of the circle that is described by triangle ABC equals to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is equals to 1.907 units in its length. Repeat again, I should find out that the radius of this circle R that is inscribed by triangle ABC, it is equal to 1.907 units. Our test is to find out the area of this green shape. So this is sector POL. What is a sector? A sector is a portion of a circle enclosed by two radii and the arc LP between them. I repeat again. The green shape AOB is a sector, is a portion of this circle enclosed by two radii and arc AB between them. The two radii are defined as the legs of the sector. So angle theta is located between the legs of this sector, and the area of this sector AOB, it is equals to pi r squared. This is the area of the circle that contains the sector, times the angle between the legs of the sector that is theta over 360 degrees. Repeat again. A sector is a portion of a circle enclosed by two radii and arc AB between them. The sector AB equals to pi r squared. This is the area of this circle that contains the sector, times the angle between the legs of the circle that is theta over 360 degrees. Our task is to find out the area of this green shape. So what is the area of this green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of quadrangle POLC minus the area of this sector POL. And repeat again, the area of this green shape equals to the area of quadrangle POLC minus the area of this sector POL. So write it down. The area of the green shape, that is the area that we are looking for this question, is equal to the area of this quadrangle POLC minus the area of this sector POL. The area of the green shape equals to the area of quadrangle POLC minus the area of sector POL. The rounded line above POL is the sign for a sector. It means sector POL. In the next step, we'll join points Q and C together by a straight line. Join points O and C together by a straight line. This is point O. By joining points O and C, we divided quadrangle POLC into two parts. This is the first part, this is the second part. It is very clear that the area of quadrangle POLC must be equal to the sum of the areas of the two shapes that it consists of. Quadrangle POLC consists of this shape that is actually the right triangle OLC plus the second shape that is the right triangle OPC. So the area of triangle and the area of quadrangle POLC must be equal to the area of the first shape, that is the area of the right triangle OC, plus the area of this second shape, that is the area of triangle right triangle OPC. So write it down. Actually found out that the area of this quadrangle POLC is equals to the area of this right triangle OPC plus the area of the second shape that is consists of, this is actually the area of the right triangle OLC. This right triangle OLC. it again. There of quadrangle P, O, and C is equals to there of the first shape that consists of is actually there of the right triangle P, O, and C plus there of the second shape that is consists of is actually there of triangle O and C. Minus there of this sector PON. According to the formula that I presented to you a couple minutes ago, there of this sector POL must be equal to there of the circle that contains this sector, that is actually pi r square, r is the radius, times the angle between the legs of the sector, that is 139.632 degrees over 360 degrees. So if you found out that the area of sector POL in total it is equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is actually 139.632 degrees or 360 degrees. What is this right triangle POC? There is this triangle POC. Is equal to the base of the triangle that is OP, and OP is R, times the height that is PC, and PC is 5, divided by 2. So in total, there of this right triangle POC equals to 5R over 2. There of the right triangle POC equals to 5R over 2 square units in its size. Plus the area of this right triangle OLC. The area of this right triangle OLC equals to the base OL, that is R, times the height LC, that is 5, divided by 2. So in total, you found out that the area of this right triangle OLC is also equals to 5R over 2 square units in size. Minus the area of sector POL. In total, the area of sector POL equals to pi r squared times 139 plus times 139.632 degrees over 360 degrees. We already found out that the radius of the circle R equals to 1.907. We'll substitute R in this equation by 1.907. And get that in total the area of sector POL equals to pi times r squared. R is 1.907, and therefore r squared is 1.907 squared times 139.632 degrees over 360 degrees. We have here 5R over 2 plus 5R over 2. We take 2 as a common factor out of those two expressions, and we get that 5R plus 5R is 10R, and 10R over 2, 10R over 2 is 5R. And so the value of those two expressions, it is equals to 5R. Minus the area of sector POL equals to pi times 1.907 squared times 139.632 degrees over 360 degrees. Actually, the value of this expression in total is equal to 4.387 square units in size. So the area of the green shape equals to 5R minus 4.378, 5R minus 4.387 square units. R is 1.907, and therefore 5R is 5 times 1.907, that actually equals to 9.535 minus 4.387. 9.535 minus 1.387 is equal to 5.148 square units in its size. So we should find out that the area of the given shape equals to 5.148 square units in its size. The area of this given shape equals to 5.148 square units in its size. We finished with the first question. In the next step, we'll present to you the second question, and we'll solve the second question by using 3 different methods. Our task in the second question is to find out the area of this square ABCD. So in the void area square ABCD, this is again DB is the diagonal of square ABCD. This is again BDP, that is equals to 30 degrees in its size. This is again PBC, this is also equals to 30 degrees in its size. This is line 7 PB, is equals to 5 units in its length. Again, our task is to find out the area of this square ABCD. So first of all, we know that the diagonals of any square bisect the angle of the squares. Yeah, the diagonal of any square bisect the angles of the square. Diagonal DB bisect the angle ABC. ABC equals to 90 degrees. Angle ABC equals to 90 degrees. Diagonal DB bisect the angle ABC. So the first half is 45 degrees. The second half, this is the second half of angle ABC, that is also equals to 45 degrees. But this angle equals to 30 degrees, and therefore the missing angle must be equal to 15 degrees in its size. Likewise, diagonal BD bisect angle ADC. So this is the first half, is equals to 45 degrees. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size. Actually, this is the first half. This is diagonal DB. This is the first half of angle ADC. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size. Likewise, this is the second half of angle ADC, that equals to 45 degrees in its size. So in triangle BDP, this is triangle BDP. 30 degrees plus 15 degrees is 45 degrees, and therefore this surface area must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Okay, so in the next step we will do a construction. That is to say, from the vertex C of square ABCD, from the vertex C of square ABCD, this point, we go angle bisector of angle DCB. Okay, again, from point C, we go angle bisector of angle DCB. Angle DCB is of course a right angle. Angle bisector, this angle bisector bisect angle DCB, so the first half must be equal to 45 degrees inside, and this is the second half, this also must be equal to 45 degrees inside. In the next step, we'll extend line segment DP until it touches the angle bisector. And we'll find the touching point of the extended line segment DP with this angle bisector. This point is point Q. In the next step, we'll join points B and Q together by a straight line. This is triangle DQC. This triangle DQC, 15 degrees plus 45 degrees is 60 degrees, and therefore this third second must be equal to 120 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two triangles can go into each other according to side against side rule. This is to say, we prove that triangle QVC can go to this triangle DQC according to side angle side rule. So, while those two triangles can go into each other. while those two triangles can go into each other. First of all, side BC of triangle PQC is equal to side DC for this triangle DQC. They are both the sides of square ABCD and therefore they are equal to each other. And again, side BC of triangle QBC equals to side DC of triangle DQC. They are both the sides of a square and therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees and therefore they are equal to each other. So finally, this is angle BQC. In triangle QBC, and it is equal to this angle, the angle DCQ. In triangle DQC. Repeat again. Angle BQC in triangle QBC equals to angle DCQ in triangle DQC. They are both equal to 45 degrees and therefore they are equal to each other. And finally, QC is a common side that belongs to both triangles. Repeat again, side QC is a common side that belongs to triangle BCQ, and QC also belongs to triangle CQD. So you can write down that QC equals to itself as a common side that belongs to both triangles. So QC equals to itself as a common side that belongs to both triangles. So if you prove that those two sides and the angle that is included between those two sides, this triangle PQC, are possibly equal to those two sides and the angle that is included between those two sides in this triangle DQC. And therefore those two triangles can go into each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in this triangle QBC are possibly equal to those two sides and the angle that is included between those two sides in this triangle DQC. And therefore those two triangles can go into each other according to side angle side rule. So right now we should follow the triangle QBC congruent. This is the sign of congruence to triangle DQC according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that those two corresponding angles must be also equal to each other in their sizes. That is to say, angle QDC, this triangle CDQ is equal to this angle, this is angle QBC, this triangle BCQ. Again, from the fact that those two triangles can go into each other, we learn that those two corresponding angles must be also equal to each other and their sizes. But we already found out that angle QDC equals to 15 degrees in size, so we can write here that angle QDC equals to 15 degrees in size. And from this equation, 15 degrees equals to angle QDC equals to angle QBC, we derive that angle QBC also equals to 15 degrees in size. Those two sides of the equation are equal to each other. So the missing angle QBC is also equals to 15 degrees in its size. This is the missing angle QBC. It equals to 15 degrees in its size. Diagonal DB bisect angle ABC. This is the first half of angle ABC, that is 45 degrees. This is the second half. The second half must be also equal to 45 degrees. 15 degrees plus 15 degrees is 30 degrees, and therefore this first missing angle must be equal to 15 degrees in its size. 15 times 3 is 45. That is the size of this second half. In the next step, we'll prove, but before that, we extended the third line DP. This is the third line DP. We extended the third line DP by third line, and we got line 7 DQ. When you extend the third line by third line, the result DQ must be also a third line. DQ is a third line. We focus on the right side of the third line DQ at point P. So here the sum of the angles must be equal to 180 degrees. This is to say the sum of the angles on the right side of the third line DQ at point P must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the third line is equal to 180 degrees. So which angles we have at the right side of the third line DQ at point P? We have this angle that is 135 degrees plus this missing angle, and told them the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 45 degrees in size. So, this is the right triangle PQB. This right triangle PQB, 45 degrees plus 15 degrees is 60 degrees. And therefore this third missing angle must be equal to 120 degrees in size according to the rule that the sum of the angles in the triangle is equal to 180 degrees. So this missing angle must be equal to 120 degrees in its size. Likewise, this is the right triangle BQC. The right triangle BQC, 45 degrees plus 15 degrees is 60 degrees. Therefore, this third missing angle must be equal to 120 degrees in its size, according to the same rule. In the next step, we'll prove that those two triangles can go into each other according to angle side angle rule. That is to say, we'll prove that triangle, this is triangle PQC, that it can go to this triangle PQB according to angle side angle rule. So to prove that the triangle PQC can go to this triangle PQB according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 120 degrees and therefore they are equal to each other. So here this is angle BQC. In triangle BQC is equal to this angle, the angle PQB. And triangle BPQ. And again, we should find out that angle BQC triangle BQC equals to angle PQB triangle QPB. They are both equal to 120 degrees and therefore they are equal to each other. In addition, side QB is a common side that belongs to both sides. Side QB definitely belongs to triangle QBC and side QB definitely belongs to triangle VQP. So we can write down that QB equals to itself. It's a common side that belongs to both triangles. That QB is a common side that belongs to both triangles. So QB equals to itself is a common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees and therefore they are equal to each other. So here, this is angle QBC. The triangle BQC, and it is equal to this angle. This is actually angle PBQ. The triangle QPB. Okay, again, I shall find out that angle QBC, triangle BQC equals to angle PBQ and triangle QPB. They are both equal to 15 degrees and therefore they are equal to each other. So we shall find out that those two angles and the side that is included between those two angles is actually side QB in this triangle QBC are corresponding equal to those two angles, and the side that is included between those two angles that is also side QB in this triangle PQB. Therefore those two triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in this triangle QBC are corresponding equal to those two angles, and the side that is included between those two angles in this triangle PQB. Therefore, those two triangles can go into each other according to angle side angle rule. So, write it down. So, found out actually the triangle BQC congruent. This is the side of congruent. To triangle PQB according to angle side angle rule. And for the fact that those two triangles can go into each other, we realize that their corresponding sides must be also equal to each other. Side PB of triangle PQB is the corresponding side of side BC of the triangle BQC. Why PB is the corresponding side of BC? Because the triangle PQB, side PB is located in front of this angle that is equal to 120 degrees in size. Likewise, in triangle BQC, BC is also located in front of this angle that is equal to 120 degrees in size. Therefore, side PB is the corresponding side of side BC. And we have the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides, that is to say BC and PB, must be also equal to each other in their lengths. We found out that BC equals to PB. And again, BC equals to PB. According to what is given in the question, PB equals to 5. So we can write here that PB equals to 5. And for this equation, BC equals to BB equals to 5. We write that BC also equals to 5 units in itself. Those two sides of the equation are equal to each other. So BC also equals to 5. Our test is to find out this square ABCD. You actually know that the area of any square equals to the length of one side squared. Again, the area of any square equals to the length of one side squared. And therefore, the area of square ABCD must be equal to the length of one side squared. That is to say, it is BC squared. But BC is 5, therefore BC squared is 5 squared, that is 25 square units in its size. So if we found out that area of this square ABCD is equal to 25 square units in its size. We finish with the first method. In the next step, I'll present to you how to find out the area of this square ABCD according to the second method. So, diagonal DB, a rectangle of square ABCD. This is the first half of angle ABC, equals to 45 degrees. This is the second half of angle ABC. It also equals to 45 degrees in size. But this angle equals to 30 degrees, and therefore this missing angle also equals to 15 degrees in size. Likewise, diagonal BD must rectangle ADC, so this is the first half is equals to 45 degrees in its size. And this is the second half of angle ADC, that also equals to 45 degrees in its size. But this angle equals to 30 degrees, and therefore this missing angle must equal to 15 degrees in its size. In triangle DBP, 30 degrees plus 15 degrees is 45 degrees, and therefore this third missing angle must be equal to 135 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will do a construction. That is to say, we will draw a circle around square ABCD. Okay, again, we will draw a circle around square ABCD in such a way that point A will be the center of the circle that we will draw, and the radius of the circle will be equal to side length of square ABCD. Again, point A will be the center of the circle, AB will be the radius. We find AB is x. AD is also the radius of the circle that we draw. It is also equals to x units in itself. So actually, this is the circle that we draw around square ABCD. So I mentioned before, point A is the center of the circle, AB is the radius, AD is also the radius. The radius of the circle is equal to the side length of square ABCD. Okay, AB is the radius of the circle. The radius of any circle has two edges. The first edge of any radius must be located on the center of the circle, and the second edge must be located on the circle itself. This is the definition of a radius. Therefore, point B must be located on the circle itself. The circle passes from point B. AD is also the radius. Again, the radius of any circle has two edges. The first edge is point 8, it is the center of the circle, and the second edge is point D, must be located on the circle itself. It is true for any radius, and therefore it must be true and the radius AD. The first edge must be located on the center of the circle, and the second edge must be located on the circle itself. Therefore, the circle passes through point D. We already found out that angle DPB equals to 135 degrees in its size. This is angle DPP that equals to 135 degrees in its size. This is center angle DAB. This is center angle DAB. What is the size of this center angle DAB? You know that the sum of the angles around any point is equal to 360 degrees. Okay, again, the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point A must be equal to 360 degrees. This is a right angle plus the missing angle. In total must be equal to 360 degrees. And therefore this missing angle must be equal to 230 degrees in its size. So center angle DAB equals to 270 degrees in its size, and it is located, it's subtend on chord DB. Again, center angle DAB, the big center angle DAB equals to 230 degrees in its size, and it's subtend on chord DB. Likewise, this angle DBP, it is also subtend on the same chord DB, and it equals to 135 degrees in its size. So here you can implement rule 13. According to rule 13, the center angle is twice as large as the peripheral angle subtended on the same chord. The drawing of a circle, this is peripheral angle ACB, that's subtended on chord AB, and it equals to theta degrees in size. Likewise, this is center angle AOB, that's subtended on the same chord called AB. And because of the fact that those two angles are both subtended on the same chord called AB, the size of center AOB must be twice as large as the size of this peripheral angle ACB. The size of this peripheral angle ACB is theta, and therefore the size of center angle AOB that's subtended on the same chord called AB must be equal to 2 theta. So in the drawing we have center angle BAB that's subtended on chord DB, and it equals to 270 degrees in its size. We have also angle DBP that's subtended on the same chord called DB. So those two angles are both subtended on the same chord called DB. And the size of center angle DAB equals to 270 degrees. That is twice as large as the size of this angle DBP that's subtended on chord DB. They are both subtended on the same chord, and the size of the center angle is twice as large as the size of this angle DBP. So angle DBP obeys to rule 13 because it is half of the center angle that's subtended on the same chord called DB, therefore it must be a peripheral angle. Okay? Because of the fact that angle DBP obeys to rule 13, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. Okay, therefore angle DBP, it must be a peripheral angle. is a peripheral angle. We know that all the three vertices of any peripheral angle lie on the circle itself. Peripheral angle DBP is three vertices, D, P, and B. Point D lie on the circle itself, point B lie on the circle, therefore point P, the vertex P must lie on the circle itself because it is a peripheral angle. DBP is a peripheral angle according to Rule 13. So, if we found out that the circle passes from point P, again, in conclusion, found out that the circle passes from point P. Point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, is equal to X according to our definition. This is angle ABP. Angle ABP in total equals to 45 degrees plus 15 degrees. That is 60 degrees. Angle ABP equals to 60 degrees. So in the next step, I'll copy triangle ABP in a new page and we'll analyze this triangle ABP. So actually, this is triangle ABP that I copied from the original drawing. We already found out that angle ABP equals to 60 degrees in size. Side AB equals to side AP in triangle ABP. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But this angle equals to 60 degrees, and therefore this missing angle must be also equals to 60 degrees in its size. 60 degrees plus 60 degrees is 120 degrees, and therefore this first missing angle must be equal to 60 degrees in its size. So all the three angles for triangle ABP are all equal to 60 degrees, and therefore it is an equilateral triangle. Right now, if you know that triangle ABP is an equilateral triangle. You know that all the sides of any equilateral triangle are equal to each other. I repeat again, all the sides of any equilateral triangle are equal to each other. So in equilateral triangle ABP, side AB equals to side BP. But according to what is given in the question, BP equals to 5 units in its length. So we can write here that BP equals to 5. And from this equation, AB equals to BP equals to 5, we got that AB also equals to 5 units in its length. This is side AB, is equals to 5 units in its length. Our test is to find out this square ABCD. What is the square ABCD? I should have known that the opening square equals to the length of one side squared. Therefore, it is the length of AB squared. But AB is 5. Therefore, AB squared is 5 square. That is 25. So, in total, we found out that the area of square ABCD is equal to 25 squares in its side. In the next step, I'll present to you how to find out the area of the square ABCD according to a third method. Diagonal DB bisect the angles of the square, so DB bisect angle ABC. This is the first half. This is equals to 45 degrees in its size. This is the second half of angle ABC that also equals to 45 degrees in size. This angle equals to 30 degrees, and therefore this angle must be equal to 50 degrees in size. And triangle BDP, 15 degrees plus 30 degrees is 45 degrees. Therefore, this quadrature must be equal to 135 degrees in its side, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We define the length of side DC. We define the length of side AD as x. Therefore, AB is also equal to x. This is a right angle, but ABCD is a square. So in the next step, we implement the Pythagoras theorem on this big right triangle DAB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So in the right triangle ADB, DB squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. So I write it down. So dB squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. dB is the missing side, so let us it is. So it's dB squared equals to AD square. AD is x, therefore AD square is x square plus AB square. AB is also x, so AB square is x square. So in total, dB square equals to x square plus x square, that is 2x square. dB square equals to 2x square. Here we take out all this equation and finally get that the missing hypotenuse dB is equal to the square root of 2 times the square root of x squared. The square root of x squared is x. So in total we should know that dB, the hypotenuse dB, is equal to the square root of 2 times x units in its length. In the next step, we will implement the law of sines in this triangle DBP. The law of sines is true in any triangle. This is triangle ABC that would be any triangle. Side AB of triangle ABC equals to C units in its length. Side BC equals to A units in its length. Side AC equals to B units in its length. This is again BAC is equals to capital A degrees inside. This is again ABC, this is equals to capital B degrees inside. This is again ACB, this is equals to capital C degrees inside. So in this triangle ABC that would be any triangle according to the law of sines, the following equation is true. That A over sinus A equals to B over sinus B equals to C over sinus C. Again, A over sinus A equals to B over sinus B equals to C over sinus C. So we implement the law of sines in this triangle DBP. According to the law of sines, in this triangle DBP, dB over sinus 35 degrees dB over sinus 135 degrees is equal to BP over sinus 30 degrees. And again, the triangle DBP according to the law of sines. We get that dB over sinus 125 degrees equals to BP over sinus 30 degrees. dB equals to the square root of 2 times x. Sinus 135 degrees equals to the square root of 2 times 2, and it is equals to BP, that is 5 according to what is given as the question. For sinus 30 degrees, sinus 30 degrees is 1/2. So in total we should know that square root of 2 times x over square root of 2 over 2 equals to 5 over 1/2. 5 over 1/2 is 10. You will move 2 to the numerator, square root of 2 to the denominator, and get that 2 times square root of 2 times x or square root of 2 equals to 10. So in total this expression equals to 2 times square root of 2 times x or square root of 2. So we have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. So in this side of the equation we left only with 2x, that is equal to 10. Here we divide this equation by 2 and find again that x equals to 8 over 2, that is 5. So here, x equals to 5. One side of square ABCD equals to 5 units in its length. Our task is to find out this first square ABCD. We know that the of square equals to the length of one side squared. The length of one side of square ABCD is x, therefore the length squared is x squared. X is 5, so x squared is 5 squared, that is 25. Square units in size. So in all the three methods we arrive to the same result, that the area of this square ABCD, that is the area that we were looking for in this question, is equal to 25 square units in size. So we finish with the first method. In the next step, I will start with the lecture. We'll start with the first question, of course. Our test, the first question is to find out the area of this V shape. So in the drawing we have a circle that is enclosed by triangle ABC. We know that side AB of triangle ABC equals to 6 units in itself, side ABC equals to 9 units in itself, and side AC equals to 7 units in itself. Again, our test is to find out the area of this V shape. So first of all, we define the size of this area is CB, is theta. And then we implemented the law of cosines in this triangle ABC. The law of cosines is true in any triangle. This is triangle ABC, this could be any triangle. Side AB of triangle ABC equals to 1 unit in itself, side AC equals to 1 unit in itself, side BC equals to 3 units in itself. This is angle BC, this is equal to theta degrees in size. So in this triangle ABC, the following equation is true. That cosine theta equals to a square plus b square minus c square over 2 times a times b. Again, cosine theta equals to a square plus b square minus c square over 2 times a times b. Can you implement the law of cosines in this triangle ABC according to the law of cosines? Cosine theta equals to ac square plus cb square minus ab square over 2 times ac times cb. And again, entire ABC according to the law of cosines. Cosine theta equals to AC square plus CB square minus AB square over 2 times AC times CB. So cosine theta equals to AC square. AC is 7, therefore AC square is 7 square plus BC square. BC is 9, therefore BC square is 9 square minus AB square. AB is 6, therefore AB square is 6 square over 2 times AC, that is 7, times CB, that is 9. So I should remember that cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. 7 square is 49, 9 square is 81, minus 6 square, that is 36, over 7 times 9 is 63, 63 times 2 is 126. So in total, if you know that cosine theta equals to 49 plus 81 minus 36 over 126. 49 plus 81 is 130. 136 equals over 130 minus 36 over 126 equals to cosine theta. 130 minus 36 is 94, so in total we have here 94 over 126 equals to cosine theta. 94 over 126 equals to 0.7169. Cosine theta equals to 0.7169. We would like to find out the value of angle theta itself. In order to find out the value of angle theta, we will operate the opposite function of cosine, that is arc cosine, on the result of cosine theta, that is 0.7169, and this way we get the value of angle theta itself. So arc cosine of 0.7169 equals to theta, and arc cosine 0.7169 equals to 40.368 degrees. So theta equals to 40.368 degrees inside. Therefore, 180 degrees minus theta equals to 180 degrees minus 40.368 degrees, that is equals to 129.632 degrees. In the next step, we define the center of this circle. This point as point O. We define the point of tendency of tangent BC with this circle. This point as point L. Likewise, we define the point of tendency of tangent AB with this circle. This point as point Q. We define the point of tendency of tangent AC with this circle. This point as point P. The next step, we define the radius of this circle as R. Then we join points O and L together by straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle, is equals to R. The radius of L is equals to R, the radius of L is 1 to point L, that is the point of tendency of tangent BC with this circle. And now your radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is the radius of the circle, this equals to R. Point P is the point of tendency of tangent AC with this circle, and therefore this angle equals to 90 degrees, and this angle equals to 90 degrees according to the same rule, rule 1. By doing this construction, we get a quadrangle POLC. We know that the sum of the angles in any quadrangle is equal to 360 degrees. But again, the sum of the angles in any quadrangle is equal to 360 degrees. So quadrangle POLC, 90 degrees plus 90 degrees is 180 degrees, plus theta, plus the missing angle POL, in total must be equal to 360 degrees according to the rule that I mentioned. And again, in quadrangle POLC, the sum of the angles must be equal to 360 degrees. So 180 degrees plus theta plus the missing angle POL, in total must be equal to 360 degrees. Here we subtract 180 degrees from this equation. So 180 degrees will get cancelled. So we left in this side of the equation only if theta plus the missing angle POL equals to 360 degrees minus 180 degrees, it is 180 degrees. So in total, we should find out the theta plus the missing angle POL equals to 180 degrees. Here we subtract the theta from this equation, and we find out that the missing angle POL equals to 180 degrees minus theta inside. This is the missing angle POL, it equals to 180 degrees minus theta. But we already found out that angle 80 degrees minus theta equals to 129.632 degrees. So we can write here that angle POL is equals to 180 degrees minus theta equals to 129.632 degrees in its size. In the next step, we found the semi-perimeter of triangle ABC. The semi-perimeter of any triangle equals to the perimeter over 2. The perimeter of any triangle equals to the sum of three side lengths. In this case, it is 6 plus 9 plus 7. And if we divide it by 2, we get the semi-perimeter of triangle ABC. So the semi-perimeter of triangle ABC equals to the perimeter that is 6 plus 9 plus 7 over 2. 6 plus 9 is 15, 15 plus 7 is 22, 22 over 2 is 11. So the semi-perimeter of this triangle ABC equals to 11 units in its length. The next step, we found out the area of this triangle ABC according to a special formula. Actually, the outer ABC equals to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of the triangle. Now, case the semi-perimeter S is 11. A, B, and C are the side lengths of the triangle ABC. In our case, A equals to 6, B equals to 9, and C equals to 7. So the triangle ABC equals to S, that is 11, times S minus A. S is 11, A is 6, so 11 minus 6 is 5, times S minus B. S is 11, B is 9, so S minus B is 11 minus 9, that is 10, times S minus C. S is 11, C is 7, so S minus C is 11 minus 4, that is 11 minus 7, that is 4. So if you found out that the outer ABC equals to the square root of 11 times 5 times 2 times 4. The square root of 4 is 2, so we took 4 out of the root. And finally found out that the outer ABC equals to 2 times root of 2 times root of 11 times 5 times 2. 11 times 5 is 55, 55 times 2 is 110. So in total, if you found out that the outer ABC equals to 2 times root of 10 units in its times 2 times root of 110 is coincident in size. Outer ABC equals to 2 times root of 110 is coincident in size. Triangle ABC blocks the circle. Triangle ABC blocks the circle. So we have a special formula for a triangle that blocks a circle. According to the special formula, the triangle that blocks a circle is equal to S, that is the semi-perimeter of the triangle that blocks the circle, times R. R is the radius of the circle that is blocked by the triangle. Or R is the radius of the circle that is inscribed by the triangle. We already found out that the triangle ABC equals to 2 times root of 110, it's in size. S, the semi-perimeter S is 11. R is the radius of the circle that is inscribed by triangle ABC, the missing variable, so we have this it is. So in total, if you found out that 2 times root of 110 equals to 11 times R. Here we divided this equation by 11, if we found out that the radius of this circle that is inscribed by triangle ABC equals to 2 times root of 10 over 11. 2 times root of 10, 2 times root of 110 over 11 equals to 1.907 units in its length. So the radius of this circle is equals to 1.907 units in its length. Our test, so in the next step, implemented also in our drawing. According to all two, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing of a circle, this is the common standpoint point P. For the common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. According to all two, this one all two are equal to each other. That is to say PA equals to PB. So we implemented all two in our drawing. First of all, we define the length of line segment BL as A, and then we focused on this common standpoint point B. From this common standpoint point B, we have two tangents to this circle, tangent BL and tangent BQ. According to all two, they are equal to each other. That is to say, BL equals to BQ, but BL is A, therefore BQ must be also equal to A units in its length, according to all two. So AQ equals to AB minus QB. So AQ equals to AB, that is 6, minus QB, that is 8. So in total, AQ equals to 6 minus 8. Likewise, here LC equals to BC minus BL. So LC equals to BC, that is 9, minus BL, that is 8. So in total, LC equals to 9 minus 7 in its length. Then we implemented all two on the common standpoint point A. From the common standpoint point A, we have two tangents to this circle, tangent AQ and tangent AP. And according to all two, they are equal to each other. That is to say, AQ equals to AP. But AQ is 6 minus 8, AP must be also equal to 6 constraints in itself according to rule 2. Likewise, we focus on the common sum point C. From this common sum point C, we have two tangents to this circle. Tangent CP and tangent CL. And according to rule 2, they are equal to each other. That is to say, CP equals to CL. But CL is 9 minus 8, therefore CP must be also equal to 9 minus 8 in itself. AC, side AC of triangle ABC equals to 7 units in itself. AC consists of two line segments, AP and PC. Therefore, AC must be equal to AP plus PC. Okay, so AC in total equals to AP plus PC. AC equals to AP plus PC. So AC equals to AP, that is 6 minus 8, plus PC, that is 9 minus 8. So AC in total equals to 6 plus 9, that is 15. And minus A minus A is minus 2A. So in total AC equals to 15 minus 2A. AC is 7, so we subtract AC by 7. And we found out that 7 equals to 15 minus 2A. Here we subtract 7 and we added 2A to this equation simultaneously. And finally found out that 2A equals to 15 minus 7, that is 8. So 2A equals to 8. Here we divided this equation by 2 and finally found out that A equals to 8 over 2, that is 4. So here A equals to 4, A equals to 4, AQ equals to 6 minus 8, 6 minus 8, 6 minus 4, that is 2. AP equals to 6 minus 8, that is 2. PC equals to 9 minus 8, 9 minus 8 is 9 minus 4, that is 5. And LC also equals to 9 minus 8, that is 5. In the next step, this is sector POL. So what is a sector? A sector is a portion of a circle enclosed by two radii and arc LP between them. And again, the grain shape AOB is a sector. It is a portion of this circle enclosed by two radii and arc AB between them. The angle between the two radii are defined as the legs of the sector. Theta is the angle between the legs of the sector. The area of this sector will be equals to the area of the circle that contains the sector, that is pi r square, r is the radius of the circle, times the angle between the legs of the sector, that is theta, or 360 degrees. Then again, the area of sector will be equals to pi r square times theta, or 360 degrees. Our task is to find out the area of this grain shape. What is the area of this grain shape? From the drawing, it is very neat to see that the area of this grain shape equals to the area of quadrangle POLC minus the area of sector POL. Repeat again, the area of this grain shape equals to the area of quadrangle POLC minus the area of this sector POL. Repeat again, the area of the grain shape, that is the area that we are looking for in this question, it is equals to the area of quadrangle POLC minus the area of sector POL. In the next step, we join points O and C together by straight line. By joining points O and C, we divided quadrilateral POLC into two parts. This is the first part, this is the second part. It is very clear that the area of quadrilateral POLC must be equal in total to the area of the sum of the areas of the two shapes that it consists of. It consists of this first shape, that is the right triangle OC, and also consists the second shape, that is the right triangle OPC. So the area of quadrilateral POLC must be equal to the sum of the areas of those two right triangles. And this one is found that the area of quadrilateral POLC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it is equal to the area of the first shape, that is actually the right triangle POC, plus the area of the second shape, that is the right triangle OLC. Minus the area of this sector POL. According to the formula that I presented to you a couple of minutes ago, the area of this sector POL must be equal to the area of the circle that contains the sector, that is pi r square, times the angle between the legs of the sector that is 139.632 degrees or 360 degrees. Okay, again, the area of the sector POL. In total, it is equal to the area of the circle that contains the sector, that is pi r square, times the angle between the legs of the sector that is 139.632 degrees over 360 degrees. What is the area of this triangle POC? The area of the triangle equals to the base of the triangle times the height over 2. We choose the base as PO. PO is the reduced arm. PC equals the height PC is 5. And therefore in total the triangle POC equals to the base R times the height 5 over 2. Is equals to 5 R over 2. The area of the triangle POC equals to 5 R over 2. Plus the area of this triangle OSC equals to the base OL that is R times the height LC that is 5 over 2. So that is equals to 5 R over 2. So the area of triangle OLC also equals to 5 R over 2 minus the area of sector POL is equals to pi r squared times 129.632 degrees over 360 degrees. R is 1.907, therefore R squared is 1.907 squared. So in total, pi r squared is pi times 1.907 squared times 129.632 degrees over 360 degrees. 5 r over 2 plus 5 r over 2 is 5 r. The value of this expression in total equals to 4.387 square roots in its size. R is 1.907, therefore 5 r is 5 times 9.07, that is 9.535, minus 4.387, that is equals to 5.148. Total, if you follow the area of this measure, that is the area that you are looking for this question, is equal to 5.148 square roots in its size. So we finish with the first question. In the next step, I repeat on the second, on the solution of the second question in 3 different methods. Our task in the second question is to find out the area of this curve square ABCD. So in the one square ABCD, this is diagonal DB of square ABCD. This is angle BDQ, this is equal to 30 degrees in its size. Likewise, this angle BC, this is also equal to 30 degrees in its size. This is line PB, this is equal to 5 units in its length. Again, our task is to find out the area of this square ABCD. So first of all, we know that the diagonals of a square bisect the angles of the square. Again, the diagonals of a square bisect the angles of the square. Diagonal DB bisect the angle ABC. ABC in total is 90, so the first half, this is the first half that is 45 degrees. This is the second half, this is also 45 degrees in its size. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size. This missing angle must be equal to 15 degrees in its size. Likewise, diagonal BD bisect the angle ADC. This is the first half of angle BDC, that is 45 degrees. This is the second half, it is also 45 degrees. But this angle equals to 30 degrees, and therefore this missing angle is equal to 15 degrees in its size. So In the next step, we did a construction, that is to say, from point C, we draw angle bisector of angle DCB. Angle DCB equals to 90 degrees. So the angle bisector bisects angle ADCB. This is the first half, that is 45 degrees. This is the second half, that is also equals to 45 degrees in size. The next step, we extended 970p by straight line until it touches the angle bisector. We define the touching point of the extended 970p with this angle bisector. This angle is point Q. So, in triangle DBP, this angle equals to 15 degrees, this angle equals to 30 degrees. 15 degrees plus 30 degrees is 45 degrees, and therefore this quadrant angle must be equal to 135 degrees inside, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. DP is a straight line. When you extend a straight line by straight line, the result DQ is also a straight line. If you focus on the right side of the straight line DQ at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. Which angles we have at the right side of DQ at point P? We have this angle that is 135 degrees, plus this VC angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this VC angle must be equal to 45 degrees. So 135 degrees plus 45 degrees is 180 degrees. That is the sum of the angles on the right side of the straight line DQ at point P. So this VC angle equals to 45 degrees in size. So, in the right triangle, it is not a right triangle, in triangle PBQ, this angle equals to 45 degrees. So not know yet that this angle equals to 15 degrees, so it is. So, in triangle DQC, this angle equals to 15 degrees, this angle equals to 45 degrees, 15 degrees plus 60 degrees, 15 degrees plus 45 degrees is 60 degrees, and therefore this missing angle must be equal to 120 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two triangles can go into each other according to side angle side rule. So what those two, this is to say the right triangle BQC can go into the right triangle CQD according to side angle side rule. So why those two triangles can go into each other? First of all, side DC of triangle DQC is equal to side CB of triangle BQC. They are both the sides of a square and therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees and therefore they are equal to each other. And finally, QC is a common side that belongs to both triangles. So we can find out that QC equals to itself as a common side that belongs to both triangles. So if you prove that those two sides and the angle that is included between those two sides in this triangle BQC are corresponding equal to those two sides, and the angle that is included between those two sides in this triangle BQC. And therefore, those two triangles can go into each other according to side angle side rule. And for the fact that those two triangles can go into each other, we learn that those two corresponding angles must be equal to each other in their sizes according to the rule that corresponding angles in one triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their sizes. So, angle QDC, triangle QDC equals to angle QBP, triangle QBC, triangle QBC. But we already found out that this angle equals to 15 degrees inside, angle QDC equals to 15 degrees inside. So we can write that angle QDC equals to 15, and from this equation 15 equals to angle QDC equals to angle QBC, we derive that angle QBC also equals to 15 degrees in its side. Those two sides of the equation are equal to each other. Angle QBC equals to 15 degrees in its side. This is angle QBC, this equals to 15 degrees in its side. So, diagonal DB bisect angle ABC. This is the first half, that is 45 degrees. This is the second half, that is also 45 degrees. This is the second half, that is also 45 degrees in its side. So 15 degrees plus 15 degrees is 30 degrees, and therefore this third angle was equal to 15 degrees in its side, plus 15 times 3 is 45. So in triangle BPQ, 15 degrees plus 45 degrees is 60 degrees, and therefore this third angle must be equal to 120 degrees in its side, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two triangles can go into each other according to angle side angle rule. That is to say, we prove that triangle PPQ can go into this triangle PQC according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 180 degrees, and therefore they are equal to each other. In addition, QB is a common side that belongs to both triangles, so I can write out that QB equals to itself is a common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees, and therefore they are equal to each other. So we should find out that those two angles and the side that is included between those two angles in this triangle QBC are corresponding equal to those two angles, and the side that is included between those two angles in this triangle PQB. And therefore, those two triangles can go into each other according to angle side angle rule. From the fact that those two triangles can go into each other, we know that PB, side PB, triangle PQB, is equal to side BC, triangle BQC. Those two sides are corresponding sides, and therefore they are equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides PP, PB and PC must be also equal to each other in their length. So we found out in total that side BC triangle QBC equals to side PB triangle QPB. But according to what is given in the equation, PP equals to 5. So we can write that BP equals to 5, and from this equation BC equals to BB equals to 5. We will derive that BC also equals to 5 units inside. Those two sides of the equation are equal to each other. So BC equals to 5. BC, this is side BC, is equals to 5 units in its length. Our task is to find out the area of this square ABCD. Actually, we know that the area of any square equals to the length of one side squared. So it is the length of side BC squared. It is BC squared. BC is 5, therefore BC squared is 5 squared, that is 25. So if we found out that the area of this square ABCD equals to 25 square units inside. We finish with the first method. In the next step, I repeat on the solution of the second method. Diagonal DB bisect angle ABC. This is the first half, that is 45 degrees. This is the second half, that is also 45 degrees. But this angle equals to 30 degrees, and therefore this piece angle must be equal to 15 degrees in its side. Likewise, diagonal BD bisect angle ADC. This is the first half, that is 45 degrees. And this is the second half. It also equals to 45 degrees in size. but this angle equals to 30 degrees, and therefore this piece angle must be equal to 15 degrees in size. In triangle BDP, 30 degrees plus 15 degrees is 45 degrees, and therefore this third piece angle must be equal to 135 degrees in size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we did a construction. That is to say, we draw a circle around square BCD in such a way that point A will be the center of the circle, and the side length of square BCD will be the radius of the circle. Repeat again, we draw a circle in such a way that point A will be the center of the circle, and the side length of square BCD will be the radius of the circle. So AB is the radius, equals to x according to the definition. AD is also the radius of the circle, that is equal to x. So here, this is the circle that we draw around square BCD. So as I mentioned before, point A is the center of the circle. AB equals to AD, the radius of the circle. So AB is the radius of the circle. We know that the radius of any circle has two edges. The first edge of any radius of any circle lie on the center of the circle, and the second edge of the radius of any circle lie on the circle itself. But again, the first edge of the radius of any circle lie on the center of the circle, and the second edge of the radius of any circle lie on the circle itself. Therefore, point B must lie on the circle itself. That is to say, the circle passes for point B. Likewise, we have the radius AD. The first edge of radius AD must lie on the center of the circle. The second edge of radius AB must lie on the circle itself. It is true for any radius, and therefore it must be true also on the radius AD. So point D lie on the circle itself. That is to say, the circle passes for point D. So we know that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point A must be equal to 360 degrees. This angle equals to 90 degrees. It is one angle of the square. Therefore, this piece angle must be equal to 270 degrees in size, because 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles around any point. This is the angle DBP, that is 135 degrees in size. Angle DBP equals to 135 degrees in size. So this is center angle DAB, the big center angle DAB equals to 270 degrees in size, and the subset are called DB. Again, the big center angle DAB equals to 270 degrees in size, and the subset are called DB. Likewise, we have this angle DBP, is equals to 135 degrees in size. It is half of the size of this angle. 270 degrees over 2 is 135 degrees, and subset on the same chord called AB. So those two angles are both subset on the same chord called DB. This is the center angle. This is angle DBP. So you can implement rule 13. According to rule 13, the center angle is twice as large as the peripheral angle subtended on the same chord. Therefore, you have a circle. This is peripheral angle ECB. This is equal to 30 degrees in size, and it's subtended on chord AB. Likewise, this is center angle OB. It's subset on the same chord called AB. And because of the fact that those two angles are both subset on the same chord called AB, the size of the center angle OB must be twice as large as the size of this peripheral angle ECB. The size of peripheral angle ECB is theta, and therefore the size of the center angle OB must be equal to 2 theta. So you can actually implement rule 13 in our drawing. This is an triangle DAB. This equals to 270 degrees in its size and subtend of 4 dB. Likewise, this is again DBP. This is half of this triangle. 270 degrees over 2 is 135 degrees. Again, DBP subtend on the same chord called DB. So those two angles, they are both subtend on the same chord, and the center angle is half of this angle DBP. And the center angle DB is half of the size of this angle. The center angle DB is twice as large as peripheral angle DBP, and they are both subtend on the same chord called DB. So actually, angle DBP obeys to rule 13 because it is half of the size of the center angle, and it's subtend on the same chord called DB. According to rule 13, if we have a center angle and the peripheral angle that subtend on the same chord, the size of the center angle must be twice as large as the size of the peripheral angle. The peripheral angle DBP subtend on 4 dB, and it equals to 130 degrees in its size. Likewise, center angle DAB subtend on the same chord called DB, and it is twice as large as this angle. 135 degrees times 2 is 270 degrees. That is the size of the center angle. And because of the fact that the size of the center angle DAB is twice as large as the size of angle DBP, and they are both subtend on the same chord called DB, it obeys to rule 13. Because of the fact that angle DBP obeys to rule 13, it must be a peripheral angle. Angle DBP is a peripheral angle. We know that all the three vertices of a peripheral angle lie on the circle itself. Again, all the three vertices of any peripheral angle lie on the circle itself. So vertex D lie on the circle of peripheral angle DBP, vertex B of peripheral angle DBP lie on the circle. So the vertex P of peripheral angle DBP must lie on the circle itself. That is to say, this circle passes for point P. Point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, is equal to X. So this is angle ABP, is equal to 45 degrees plus 15 degrees, it is 60 degrees. And again, angle ABP equals to 60 degrees inside. In the next step, I copied the triangle ABP in a new page and we analyze this triangle ABP. Actually, this is triangle ABP that I copied from the original drawing. We already found out that angle ABP equals to 60 degrees in size. In front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, according to the rule that in front of equal sides in the triangle, there are equal angles. So those two angles must be also equal to each other in their sizes. So they are located in front of those two equal sides. But this angle equals to 60 degrees, and therefore this missing angle must be also equal to 60 degrees in size. So in triangle ABP, 60 degrees plus 60 degrees is 120 degrees, and therefore this first missing angle must be equal to 60 degrees in size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. In triangle ABP we have three angles, they are all equal to 60 degrees, and therefore triangle ABP is an equilateral triangle. We know that all the sides of any equilateral triangle are equal to each other. So in triangle ABP, side BP equals to side AB. Side BP equals to side AB. But according to what is given in the question, BP equals to 5. And I tell that BP equals to 5, and from this equation AB equals to BP equals to 5, we know that AB equals to 5. Those two sides of the equation are equal to each other. So AB equals to 5. So one side of square ABC equals to 5 units in itself. Note that the opponent square equals to the length of one side squared. That is to say, it is AB squared. AB is 5, so AB squared is 5 squared, that is 25. So according to the second method, we found out that there of this square ABC equals to 25 units in size, exactly as we found out in the first method. to the same result. So we finish with the second method. The next step, I'm going to how to find out the square ABCD according to the first method. Diagonal DB bisect angle ABC. This is the first half of angle ABC, that is 45 degrees. This is the second half. It is also 45 degrees, but this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size. So 15 degrees in triangle BDP, 15 degrees plus 30 degrees is 45 degrees, and therefore this third missing angle must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. This is one angle, one of the angles of square ABCD, therefore it is equal to 90 degrees in its size. We define side AB of square ABCD is x, so AD also equals to x. The next step, we implemented the Pythagoras theorem on this triangle DAB. According to the Pythagoras theorem, in any triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in the triangle DAB, it means that DB squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. Again, the triangle BD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. BD is the missing side of electricity, so it is DB squared equals to AD squared. AD is x, therefore AD squared is x squared plus AB squared. AB is also x, therefore AB squared is x squared. So in total DB squared equals to x squared plus x squared, that is 2x squared. DB squared equals to 2x squared. Here we took out of this equation, and found out the DB equals to the square root of 2 times the square root of x squared. The square root of x squared is x. So in total DB equals to the square root of 2 times x units in its length. In the next step, implemented the law of sines in this triangle DBP. The law of sines is true in any triangle, therefore can implement the law of sines in this triangle BDP. For the law of sines, this is triangle ABC that could be in a triangle. Side AB equals to C units in itself, side AC equals to B units in itself, side BC equals to A units in itself. This is again BAC that equals to capital A degrees inside. This is again ABC that is equals to capital B degrees inside. This is again ACB that is equals to capital C degrees inside. So in this triangle ABC, that could be any triangle. According to the law of sines, the following equation is true, that A over sinus A equals to B over sinus B equals to C over sinus C. Again, A over sinus A equals to B over sinus B equals to C over sinus C. So we can implement the law of sines in our drawing. According to the law of sines, in triangle BDP, the following equation is true. The DB over sinus 135 degrees equals to BP over sinus 30 degrees. Again, DB over sinus 135 degrees equals to BD over sinus 30 degrees. And again, according to the law of sines, in triangle BDP, BD over sinus 135 degrees equals to BP over sinus 30 degrees. BD is square root of 2 times x, and BP is 5. Again, BD is square root of 2 times x, BP is 5. Square root of sin sinus 135 degrees is square root of 2 over 2, sinus 30 degrees is 1/2. So total square root of 2 times x over square root of 2 over 2 equals to 5 over 1/2. 5 over 1/2 is 10. Here we moved 2 to the numerator and square root of 2 to the denominator, so in total the value of this expression equals to 2 times square root of 2 times x over square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled, and inside of the equation we left only 2x, so 2x equals to 10. Here we divided this equation by 2 and finally found out that x equals to 10 over 2, that is 5. Our test is to find out the area of this square ABCD. You know that the opening square equals to the left of one side squared. The left of one side is x. So the left of one side squared is x squared. So the square ABCD equals to x squared. But x is 5, therefore x squared is 5 squared. That is 25. So all the three methods, we found out that they have this square square ABCD, that is the R that we are looking for this question, is equal to 25 squares in its size. Okay, thank you very much.